We're going to introduce one of the most important and efficient data structures for searching and sorting, and that is the binary search tree. Or in short, we'll just refer to it as BST. And by the end of this video, you're going to understand what a binary search tree is and how insertion and deletions operations work in a binary search tree. So the first thing we're going to look at is what is a binary search tree, and as you already know so far is that it's a special type of a binary tree where each node has at most two children. So we have a left child and a right child, and this is an example of a binary search tree, where as you can see, there are only two, or rather, there are at most two children in with each of the parent nodes that exist here. So a unique feature though of a binary search tree is that the left child of a node contains a value less than the parent. So if you look at this binary search tree of ours, the left child always has a value that is less than the parent child. And while the right child can have a value that is either equal to the parent or greater than the parent, right? But the left child would always have the less value. And this property basically of a binary search tree makes searching very efficient, and it comes with an average, or rather we get an average time complexity of O of log n, provided the tree is balanced. So if the tree is balanced, it's going to have average time complexity of O of log n. Now that we've understood basically what a binary search tree is, the reason why we'd use a binary search tree is because they are great when you need to maintain basically a set of items. So, for example, if you want to numbers or strings, or you need to perform efficient operations such as search, insert, and delete, and we're going to look at these operations. And the first operation that we're going to start with is the insertion in a binary search tree. So I'm going to start here with insertion. And insertion in a binary search tree is it's a quite an easy process. Basically, to insert a new value in a binary search tree, all you need to do is that you need to start at the root and compare the value with the root node. So if this is let's have this as our binary search tree here. Now, if we want to insert a value into this binary search tree, we start at the root. This is the root node here, and we compare the value with the root node. So the value that we want to insert, we compare it with the root node. And if that value is smaller, we move it to the left child. So if the value we're trying to insert is smaller, we move it here to the left child. But if that value is larger or equal to the root node, we move it to the right child right here. And we're going to repeat this process until we find an empty spot where we can insert the new value. So we're going to go through again. Do remember that a binary search tree will take at most two elements. So we'll come until we find where we're going to have this space obvious that we can use. So let's say we want to insert 13 in the following binary search tree, the one that we have here. What we'll do is we're going to start with the root node 15. So the value that we want to insert here is, we want to insert, let me use medium. So we want to insert a value 13, right? So we're going to compare 13 with what we have here as the root node. So we're going to compare the root node with the value 13. And since 13 is smaller than 15, so that means that 13 is going to belong here. So this 13 is going to move to, let's just have it like this. So it's going to move to the left child. So it's going to move to, or rather, the left subtree in this case. And the next, what we're going to do is we're going to compare this 13 with 10. And since 13 is greater than 10, that means 13, we're going to, from even the definition that we had, it's going to move to the right. It's going to move to the right here. It's going to move to the right, the right of this node, and in this subtree of that we have here. So we move to this side where we have 12, the right child where we have 12. And finally, we see that 13 is greater than 12. And since it is greater than 12, from the definition of a binary search tree again, that means now that the right child is the one that is empty. And this is where we can insert the 13. Right? So now 13 is going to come right here. And you can just change the direction a bit. So this is where we're going to have 13. And let's just have it okay. So we've inserted 13 here because this is where we found the space where we have our where we have the 12, since 13 is greater than 12 from what you've seen so far. So, and that is basically how binary insertion operation works in binary search tree. So here we've done an insertion operation. The next operation that we're going to try and do is a deletion operation. So we'll go ahead and try deletion to see how that also works in a binary search tree. So for deletion in a binary search tree, it's slightly more complex than insertion, and the reason why that is because we need to maintain the binary search tree properties. And there are three things that we consider when you are doing deletion, right? And let's look at these three things that we consider. The first case we're going to consider is the node to be deleted if it is a leaf. Yeah. So we consider these three things, and the first one is the node to be. Let's just have it in short. The node to be deleted is a leaf node, so we need to consider whether it's a leaf node. That means that if it is a leaf node, it has no children. And the second thing that we need to consider is whether the node to be deleted has one child. We also need to consider that. And the last thing we need to consider, the third thing we need to consider is whether the node to be deleted has two children. Yeah. So whether it has no child or there's an R needed here. So whether it has no children or it has one child or it has two children, it can have at most two children, of course. So in the first case where we want to delete the leaf node, we're going to get this node that we have here. Let's make a copy of it and you can have it somewhere here. So in the case of where we have we're deleting a leaf node, yeah, and this is the simplest case where let's say we want to delete 13 because this is the leaf node. This is one of the leaf node that is here. So since it is a leaf node, we can simply remove it, and the tree after deletion, what it's going to look like, it's going to look like this. So uh, that is after we have removed 13, right? And it's that easy because it is the easiest. Now the other case is when we want to delete where the second case where we're dealing with a node with one child. So let's have another copy here. So one of them needs to go back. Right. So now here we have this other node, and this is when we're dealing with deleting one child. If we're deleting a node with one child, let's say we want to delete 12 because 12 has one child here, which is 13. To delete 12, what we need to do is we need to simply replace it with its child. Its child is 13. And after deletion, how that is going to look like is we're not going to have 12, but we're going to replace it with its child. So it's going to look like this. This is when a case where we have one child. It's also have this pointers here to just indicate what we're doing. So the first thing that we have here, this is when we are dealing with a leaf node. So here we're dealing with a leaf node, and this other case that we've seen is when we are dealing with okay, that should be enough. When you're dealing with one child. Then the last case now is when you are deleting a node with two children. So this would be a good example of a node with two children. And when you want to delete a node with two children, let's say we want to delete node 15, right? So we have 15 here, and it has two children, and the two children that 15 has, how we need to handle this case is basically we need to find an in order successor. Yeah, so an in order successor is the smallest value in the right subtree. So the first thing that we need to do is we need to find an in order successor, like that. So we find an in order successor, which is the smallest value in the right subtree. So in this case, in the right subtree, the smallest value is 17. And we're going to replace the value of 15 with 17. So how that is going to look like is we're not going to have this 15 anymore. We're going to replace it with this value, which is 17, and it's going to look like this. So this is now a case where we have we're dealing with basically want to delete a node with two children, and you can simply just signify that like this. So you want to delete a node with two children. All you need to do is if you want to delete node 15, we look at the and we find an in order successor, how we find it. We're going to look at the right subtree and look for the smallest value. We're going to replace that smallest value here. So we replace then the 15 with the smallest value, and that is basically how we do deletion in the case where we only have we have two children. So that is just a quick introduction into binary search trees, and we've covered some key operations here. We've looked at insertion, and we've seen how you can insert an element here. Again, all this, the best way to understand how you can carry out an operation like insertion is just by through the definition of a binary search tree. The left child of the node always contains a value less than the parent, while the right child contains a value greater than or equal to the parent. So whatever value you want to insert, you need to do the comparison and see where it falls under. So if that value is larger than the parent, then we move it to equal to or larger than the parent. It moves to the right node. If it is less, it moves to the left. Right. So that is how we do deletion. I mean insertion. We've also seen how you can do deletion, and we've seen three cases of deletion. When you want the element that you want to delete is the left node, or rather a leaf node that you want to delete, so it has no child. In a case where the node that you want to delete has one child, in which case you're going to replace the parent with the child. And then in a case where it has two children, and also we've seen how you can do that by first finding an in order successor in such a case. So that is it up to on binary search trees, and I'll see you on the next one.